Exponential growth and decay. You've probably learned about this topic from an algebra course. We're going to take a slightly different look at it now from the calculus point of view and see where these exponential growth and decay models come from. In many natural phenomena, quantities grow or decay at a rate proportional to their size. So we're going to use this to develop what's called a differential equation, solve the differential equation generally to see what kind of model this creates. We're going to let P of t represent a population size, and we're going to suppose that the population P is growing at a rate proportional to its size. We're going to then find that function P that models the situation. All right, so if P, we're letting P represent the population size, and we're told that P is growing at a rate proportional to its size. Growing at a rate. That sounds like a derivative. The change in the population with respect to time. That's the growth rate. It's proportional to its size. What that means is we can write that dp dt is equal to some number times the population. It's proportional to its size. And now we're going to solve this, this differential equation. So this is called a differential equation because it's an equation involving a derivative. All right, so to solve this, we're going to use a technique that's called separation of variables. I'm going to get everything with P on one side of the equation and everything that isn't P on the other side of the equation. All right, so to do this, I can rewrite this equation as I'll divide by P, so I have 1 over P dt, and I'm multiplying through by dt is equal to K dt. And now I will integrate both sides. Alright, so the integral of 1 over P dp, well, that looks like a natural log. We'll assume, let's make the assumption, let P be positive. I should say greater than or equal to 0. Let the population be positive, not negative. And why I'm going to do that is, we call that the antiderivative of 1 over P dp is natural log of absolute P, and I just don't want to have to deal with the absolute. So I can write natural log of P plus a constant is equal to, now let's see, integral of K with respect to T, that would be Kt plus a constant as well. So I'll call the constant on the left C1 and the constant on the right C2. All right, now I'd like to just have one constant. So what I can do is I'll subtract to C1 from both sides, and I can write this as natural log P is equal to Kt plus just some general constant now. Now I'm going to solve for P. Rewriting this in an exponential form, I would have that P is equal to e to the kt plus c. Notice how the kt plus c is all in the exponent. Using our rules for exponents, I can write that as P is equal to e to the kt times e to the c. Now, since c is a constant, e to the c is a constant, right, because e is a constant. And so what we generally do here is we write that constant as some other, we write it as some other letter. And so what we normally do now is we write that P of t, or just P, is equal to, I'll use A, e to the kt. Now, what you learned back in algebra is that A was actually what we called the initial value or population. So we often write that P of t is P naught e to the kt, where that P naught is equal to the function evaluated at 0. Right, so we just developed that exponential model from this problem statement that we were told that P is growing at a rate proportional to its size. We were able to write a differential equation and solve it. Now I want to note one little thing here. If we go back to this original statement, dp dt is equal to kp, just here a little bit, I can solve this for k, and I can write that k is equal to 1 over p by dp dt. And this is called the relative growth rate. All right, so notice the growth rate, the dp dt, and relative divided by the population, in a sense. All right, so keep that in mind. We're going to need that in a later exercise. All right, so here's an exercise. We're told that a common inhabitant of human intestines is the bacterium E. coli. A cell of this bacterium in a nutrient broth medium divides into 2 cells every 20 minutes. The initial population of the culture is 60 cells. And we're asked several different things about this. First, we want to find the relative growth rate. So recall, just from the previous statement, that the relative growth rate is that k value, which is 1 over p by dp dt. So, well, we can start by saying we know that, how do we know that this is an exponential? Well, when we see this sort of situation where one cell divides into some number of cells every certain amount of time, that's an exponential model. So I can start off by saying, well, I know that P of t is P naught e to the kt. Alright, so basically all I need to do is figure out the k for this situation. Well, let's see. The initial population of the culture is 60 cells, and we know that the cell divides into 2 cells every 20 minutes. So if I let t, later on we have t hours. So if I let t represent the time in hours, recall that 1 hour is 60 minutes. And so then that's, in a sense, 3 divisions. All right, so we would have 1. We start with 1 cell. After 20 minutes, we would have 2 cells. After 40 minutes, we would have 2 times 2, we would have 4 cells. And after 60 minutes, or 1 hour, we would have 8 cells. All right, so what that tells me is when t is 1, the population is 8 times the original number of cells, which would be 60. All right, so P of t is P naught e to the kt. Now letting t equal 1, then I would have 480 is equal to 60 e to the k times 1. So then dividing by 60, 8 would equal e to the k. And so then solving by applying the natural log, we find that k is the natural log of 8. And that is the relative growth rate. So then an expression for the number of cells after t hours would be P of t be 60 e to the natural log 8 times t. Find the number of cells after 8 hours. Well, then p of 8 would be 60 e to the natural log of 8 times 8. And we use a calculator for this, and we get approximately 1.00646 times 10 to the 9th. And so that's, just some really large number. That's what, about 1 billion. Find the rate of growth after 8 hours. Alright, so the rate of growth, that's the dp/dt. So we need the dp/dt when t equals 8. So evaluated at t equals 8. Well, we know that p of t is 60 e to the natural log 8 times t. So then p prime of t would be 60 times e to the natural log 8t, and then times the natural log of 8 by the chain rule. So notice that that's just kp. And so then dp/dt evaluated at t equals 8 would be equal to p of 8 times the natural log of 8. And so that's approximately 2.09 times 10 to the 9th. So, what this is telling us is that at 8 hours, the population is growing at a rate of 2 billion per hour. When will the population reach 20,000 cells? Alright, so you take your original function and set it equal to 20,000. So 60 e to the natural log 8t equals 20,000. And we solve this for t. Dividing through by 60 e to the natural log 8t is equal to 20,000 over 60. Apply the natural log. So the natural log of 8 times t would be the natural log of 20,000 over 60, and divide through by natural log of 8. And so then t would be the natural log of 20,000 over 60 over the natural log of 8. And that's approximately 2.8 hours. In the previous exercise, we saw an example of exponential growth, and here we'll look at an example of exponential decay. Here we're told that strontium-90, a radioactive isotope, has a half-life of 28 days. We're then told that a sample has a mass of 50 milligrams initially. Find a formula for the mass remaining after t days. Well, we have a half-life of 28 days, and so what that means is after 28 days, half of the original amount, the original mass, remains as strontium-90. The rest has decayed radioactively and turned into other, usually other isotopes. All right, so here we have the sample, has a mass of 50 milligrams initially. Find a formula for the mass remaining after 2 days. So we know after 28 days, so we know that, I'll use again P, we know that P of 28 should equal 25. After 28 days, half of the initial sample remains. So now we have then that 50 e to the k times 28 would equal 25. Dividing through by 50, e to the 28k is 1/2, exactly 0.5. Natural log, so 28k is equal to the natural log of 0.5, and so then k is the natural log of 0.5 over 28, which is approximately negative 0.0247. So then I could write then that P of t is 50 e to the negative 0.02476 t. Find the mass remaining after 40 days. Well, that's just P of 40. P of 40 would be 50 e to the negative 0.02476 by 40. And use a calculator. And we get that approximately 18.6 grams remain after 40 days. How long does it take the sample to decay to a mass of 2 milligrams? Well, then we would have the 50 e to the negative 0.02476 t is equal to 2. And we have to solve this equation for t. Dividing through by 50, e to the negative 0.02476 t would equal 2 over 50 is 0.04. Natural log on both sides, so if we apply the natural log on the left-hand side, we would just be left with the exponent. Negative 0.02476 t is equal to the natural log of 0.04, and dividing through to solve for t, we find that t is approximately 130 days. We're asked to now sketch the graph of the mass function. So we'll put t on the horizontal axis, and we have our p on the vertical axis. And I know that I have an initial mass of 50, so what I'm going to do is I'm going to use a scale of tens. My initial value was 50, and then we get half each time period. So I'm going to be smart about it. I'm going to put 28 days as my scale. And so then this would be 56 days, 84 days, 112 days, 140 days. And so then I would have exactly half after 28 days, so that's what, 25, and then 12.5, and then 6.25, and then a little bit more than 3, a little bit more than 1.5, and we see an exponential curve. Now I won't let it continue to the left because we don't usually talk about negative time in this context, and I'll just draw this exponential curve to the right. I will show the asymptotic feature, that as time progresses, this value, in this case the amount of the strontium-90 remaining, gets closer and closer and approaches 0, but never actually reaches 0. Here's another example of an exponential model. We're told that Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, providing that this difference is not too large. And we're asked to find the temperature, we're asked to find a function t that models this situation. Okay, so let's be a little bit more careful. I'm going to let capital T represent the temperature of the object. We'll let little t represent the time. I'm going to let T sub S represent the temperature of the surrounding. And we make the assumption that that temperature is staying constant, that that surrounding temperature is relatively constant and is not too large, that the difference is not too large between the temperature of the object and the temperature of the surrounding. All right, so we want to find a function T that models this situation, that gives us the temperature of the object. All right, well, here's what we know. The rate of cooling of an object, well, that's the change in temperature with respect to time. So dt, d big T, d little t, is proportional to, is k times the temperature difference between the object and its surroundings. The temperature difference between the object and its surrounding. All right, now let's remember that the temperature of the surrounding, this is a constant. We're making that assumption that that's relatively constant. So now I'm going to solve this. Again, this is a differential equation. Again, I'm going to solve it. All right, so I can write this using the same separation of variables technique as I did in the previous exercise. I can write this as 1 over t minus t sub s dt, d capital T, let's be careful about our notation here, is equal to k d little t. And now I will integrate both sides. Alright, so let's see. Temperature difference here, T minus T sub S. Now remember, T sub S is a constant. So I can, if I were to make a substitution here, if I were to let U equal T minus T sub S, then du is simply dt. And so this looks like a natural log. And we end up now, I have to be careful here, the temperature difference, it doesn't tell us whether the temperature difference is positive or negative, so I do really need the absolute value bars here. So now the natural log absolute T minus T sub S plus a constant, I'll call it C1, is equal to the KT, little t, plus C2. Now again, I can write that as, those two constants as a single constant. And so now I have the natural log absolute of t minus t sub s is equal to kt plus a general constant. I exponentially, I rewrite this in exponential form. So then t minus t sub s is equal to e to the kt plus c. And remember, I can just write that as a more general constant times e to the kt. So I'll write this as a e to the kt. Now, since I can write it like that, where I have this factor, this constant being multiplied by the e to the kt, this will change, this can be a positive or a negative, depending on the difference between the t and the t sub s. What that means is, I don't need the absolute value bars anymore. And so I can write that t minus t sub s is simply a e to the kt. And now I can solve for t by adding the t sub s to both sides. And so t is equal to t sub s plus a e to the kt. And so this model can be used to represent Newton's law of cooling. So let's look at an example. We're told that a cup of coffee has temperature 95 degrees Celsius and takes 30 minutes to cool to 61 degrees Celsius in a room with temperature 20 degrees Celsius. Alright, so I will let T represent the time. Let little t represent the time. Now, let's be careful. We could use minutes, we could use hours. I'm going to let t represent the time in minutes. Alright, so I'm going to use Newton's law of cooling to model this situation. Well, I know the cup of coffee is temperature 95 degrees Celsius, so that means that T of 0 is 95. And it takes 30 minutes to cool to 61 degrees Celsius, so that means that T of 30 is 61 in a room with temperature 20 degrees Celsius. So that means that the surrounding temperature, that Ts, is equal to 20. So I can write now that the temperature at time t is equal to 20 plus some constant, e to the kt. That's my general model. I have to figure out the value of a, and I have to figure out the value of k. I'm first going to start with the fact that t of 0 is 95. I'm going to use that to solve for the a constant. Alright, so if t of 0 is 95, that means that 95 would equal 20 plus a e to the k times 0. Well, notice that e to the k times 0, that's e to the 0, and that becomes 1. And so then 95 is equal to 20 plus a, which implies that a is 75. Alright, so now I can revise my model a little bit. T of t is 20 plus 75 e to the kt. And now I'll use the second point. T of 30 is 61. So then 61 is equal to 20 plus 75 e to the k times 30. And now I can solve for k. Subtracting the 20 and dividing by 75, 41 over 75 is equal to e to the 30k. Natural log both sides. Natural log of 41 over 75 is equal to 30k. And so dividing through by 30, k ends up being approximately negative 0.02013. And so then my model would be that t of t is equal to 20 plus 75 e to the negative 0.02013 t. Now determine the temperature of the coffee after 1 hour. Since I've let t represent the time in minutes, then I would need to evaluate t of 60. So t of 60 would be 20 plus 75 e to the negative 0.02013 times 60. And at this point, I use a calculator to evaluate the expression, yielding about 42.4 degrees Celsius. All right, so there's a couple of examples of how we can use calculus to develop these models for natural phenomena by writing and solving a differential equation. We will look into more detail on differential equations later in this course, and you may end up taking a complete course on differential equations later on. All right, that concludes this section.